Okay, this first section will be talking about binaural effects in detection and recognition. Actually, this is the second section in the chapter, binaural and bilateral considerations in hearing aid fitting. First thing we should talk about is the cocktail party effect. This is a phenomenon by which a person is able to focus their auditory attention on a particular talker while filtering out all the background noise. There's three factors that really play a role for in creating this cocktail party effect. One would be head diffraction, which we talked about in the previous section, whereby the physical properties of the head and pinna are able to create level differences between that arrive at the two ears. Second would be binaural squelch, and this is more of a central processing effect, where when we have dichotic signals or different signals arriving at each ear, we're able to create an SNR, a representation of the SNR in our brain that's better than the SNR at either individual ear. And then third, binaural redundancy. This is where we have the same signal presented at both ears, but we get a small boost in signal-to-noise ratio here as well. So for this graph here, we can view the head diffraction effects. Imagine that we have a speaker that we're able to place at 0 degrees azimuth and move it to 30 degrees or 60 degrees or 120 degrees, with positive angles being on the side closer to the ear, whereas these negative angles are going to be the effects of the toward the ear where the speaker is not facing. So what we can see is say the speaker is positioned at a 30-degree azimuth. Let's say it's on closer to the right side, and this would be the diffraction effects here toward the right ear, and this would be the diffraction effect down here for the left ear, this dashed line for 30 degrees. And say 60 degrees, this thick black line here, that would be toward the right ear, and negative 60 degrees here, this line, that would be the left ear. A couple things we can see here would be around 3,000 hertz we have a boost compared to other frequencies. So the spectral shape is most prominent with its peak at 3,000 hertz, or right around 3,000 hertz. And that's because of the ear canal resonance. If you recall, the real ear unaided response would also have a similar peak in its spectral shape for a typical adult ear canal. From this graph, you can see that the magnitude of the differences created between the two ears can be quite significant. And it would be no surprise that because of these head diffraction effects that you could potentially have different SNRs occurring at each ear. When we have asymmetrical SNRs where there's a better SNR in one ear than the other, we're able to selectively tune in to one ear as the better SNR and ignore the ear with the worse SNR. This is referred to as the better ear effect. So you can imagine the benefits of this. Certainly, if we're assuming reasonably symmetrical hearing, then we're going to expect that the better SNR will not always occur in one ear. It'll depend on the environment that you're in. It could certainly, possibly, occur equally often in each ear. So having the ability to switch back and forth and always select the better SNR could certainly be advantageous for speech understanding and noise, or for this cocktail party effect. Let's go ahead and look at an example here in this figure. We can see that speech is arriving at around 30 degrees here, and noise is arriving at around 60 degrees here. So we have a 90-degree difference in spatial separation between the signal of interest, or the speech, and the noise. Based on the previous head diffraction effects graph, we can see that around 3,000 hertz, near the resonance of the ear canal, that the right ear gets a boost of around 19 dB because it's closer to the signal of interest, and the left ear, the noise would be getting a boost of only about 8 dB. The reason for the asymmetrical effects there are going to be related to the positioning of the signal and the noise. We can see the signal is closer to the right ear of interest, and so we'll see a greater improvement there, whereas the noise is going to be affected more by head diffraction in a negative way. It'll attenuate that signal arriving at the right ear. So if we think about how that SNR would change at the right ear compared to not having any head diffraction effects at all, we had a 19 dB improvement in the signal at the right ear, but a but only an 8 dB improvement or amplification in the noise at the right ear. So 19 minus 8 would give us 11 dB. So that's providing the head diffraction effects are providing 11 dB better SNR at the right eardrum than it would be without any head diffraction effects at all. Because of the opposite effects in the left ear, because where the noise is positioned and the speech is positioned relative to the left ear, we'll see really the opposite scenario happening. We're going to see a boost of about 11 dB for speech in the left ear, but the noise will be boosted by 20 dB. So the net effect there is a negative 9 dB SNR change in comparison to not having those head diffraction effects at all. So we will essentially have a 17 dB better signal-to-noise ratio in the right ear compared to the left ear. Fortunately, the person is able to attend, because of the better ear effect, the person can attend to just the ear with the better SNR. Unfortunately, there are going to be some downsides of this head diffraction effect. If we imagine that a person has single-sided deafness, in that scenario where the noise is located toward the good ear and the speech is located toward the dead ear, head diffraction effects will serve a net negative effect. But the opposite would be true as well. There would be a net positive effect when speech is closer to the better ear and noise is toward the dead ear. The effects of reverberation will also reduce the benefits of head diffraction, because it'll really start to deteriorate the spatial separation. The more reverberation you have, the more reflections you have, the less separated that the two sources are, the speech and the noise. Also, those with older adults, for example, with steeply sloping sensorineural losses, won't gain quite as much benefit from those interoral level differences due to head diffraction. Even though the interoral level differences would be the exact same as those with normal hearing, they just can't derive as much benefit of it. The second component to talk about for the cocktail party effect would be binaural squelching noise. This is whereby the person is able to combine these dichotic signals, these different signals at each ear, and it yields a better SNR than was present at either ear to begin with. So imagine that we have noise coming from 0 degree azimuth right in the front, and we have the signal of interest coming from 90 degrees here toward the right. And these are the waveforms, both for the signal and the noise. We can see the noise is going to be the exact same in both ears. And that's because the head diffraction effects will be identical for the right and left ear, assuming a symmetrical head. But the signal, we see that there's going to be an increased amplitude of this tonal signal in that right ear in comparison to the left ear, because again, head diffraction effects will reduce the magnitude of the signal reaching the left eardrum. Binaural squelch will essentially will allow the person's brain to subconsciously and automatically subtract the noise signal, or subtract the signals in the left ear from the right ear, eliminating the noise or reducing the noise to provide a better signal-to-noise ratio more centrally than was present at either ear. The exact mechanisms for this process are not quite clear, but they may be related to those processes seen in the superior olivary complex related to the masking level difference. So under headphones, one way we can measure the binaural squelch effect would be to use either a tonal or a speech masking level difference test. If you recall from your psychoacoustics course, the basic premise behind this is that we have two conditions. Let's talk about tone detection threshold condition. Let's say we've got a 500 Hertz masking level difference test. Under this first condition, labeled here S sub O, N sub O, we've got the signal on top here, and we've got the noise on the bottom here. It's a binaural presentation. It's a dyadic presentation. The exact same stimulus and noise are presented to both ears. So here we're measuring what is the detection threshold for this condition. But then for the other condition, we've got S sub pi, N sub O. We've phase inverted the signal, and we could do it for the noise or the signal. We wouldn't do it for both, but we could do it for either one of them. But in this condition, you can see we've flipped the signal 180 degrees. So the phase is reversed. We've got the exact same noise coming into both ears, but we've got the signal reversed only in terms of phase between the two ears, and detection threshold will be improved. If we take the threshold from this condition, subtract it from the threshold from the above condition, we can get the masking level difference. For a 500 Hertz tone for normal hearing adults, the magnitude is about 9 to 13 dB. This test can be performed using spondees as well. However, the magnitude of the effect is much smaller. For normal hearing, we're talking about probably about 5 dB. So when this test is performed clinically, it's usually done for 500 hertz pure tone. Another way we can investigate the binaural squelch effect would be to look how processing works in space, not just under earphones. In this example, we've got speech and noise coming from the front. Okay, so in this case, we might measure a certain speech and noise score. It could be a hint, I suppose, for speech and noise, SRT and noise, or it could be just some fixed SNR test where you're measuring some speech intelligibility and noise. It doesn't matter on this one. So we measure it under the condition where speech and noise are co-located. And then we also measure it under the condition where we're shifting the noise 90 degrees to the right. So we're spatially separating the noise from the speech. And there's an improvement we'll typically see in this scenario. How this improvement we can call the intelligibility level difference, or the textbook refers to it as spatial release for masking. The problem with spatial release for masking, or the intelligibility level difference under this condition, is it's going to combine both head diffraction effects and binaural squelch. So we'd like to be able to separate those out. So we can do that. This is a setup for the binaural intelligibility level difference using speakers as opposed to performing it under earphones like the masking level difference. In this condition, what we'll see is we've got speech coming from the front, we've got noise coming from the side. That's the same for both of these two conditions here. The main difference is we can see that in this condition here, the person is wearing an earplug on that right ear. There's a muff or an earplug on that right ear. And so you might initially expect that this person would do better because they're blocking out the noise on the right ear, but in this condition here, they'll actually do worse. We'll actually see a benefit by having both ears being unplugged, or both ears participating, even though the noise is directed at that right ear. In experimental designs, they may not actually plug up the right ear. They may use other ways of doing this, but that's probably the easiest way to describe it here. So this binaural intelligibility level difference paradigm, where we take away one ear and then add it back in there, here we can make sure that it's just the binaural squelch effect and that the head diffraction effects are not playing a role. And the third section we want to talk about is binaural redundancy. This refers to when we have a dyadic signals, or dyadic summation, the same signals occurring on both ears. Having the same signals occur in both ears can actually give us a small SNR improvement of around 1 to 2 dB. This can also improve speech intelligibility in quiet, so not just noise, also in quiet as well. But even those with severe losses, as well as those with more central processing issues, can benefit. So it's a very robust effect that we can see in our hearing aid clients. And so there are going to be some benefits in terms of how we implement hearing aid technologies here. If we think about so many Bluetooth accessories that we have for commercial hearing aids that allow for bilateral presentation of the telephone signal. That telephone signal is typically monaural, and so it's going to be more of a binaural redundancy effect here because we have dyadic summation. And the hearing aid manufacturers have shown that there's been an improvement for speech understanding and quiet in those situations for many hearing impaired listeners. Another effect that is implemented in some commercial hearing aid technology would be without the Bluetooth accessories, but just with a binaurally linked set of hearing aids, where on some hearing aids you can hold the phone up to one hearing aid and it streams the signal over to the contralateral hearing aid. So again, you have a monaural signal coming from the phone, but you're able to present that same signal to both ears. So you can get this nice benefit. Okay, let's move on to binaural loudness summation. This is the effect whereby when both ears are working together and they hear a sound, that sound is going to be louder than it would be if you're only hearing it with one of those ears. So in normal hearing adults, the effect is going to be dependent on stimulus level. So near detection threshold, by adding that second ear, loudness will increase by 2 or 3 dB. When you're closer to a comfortable listening level, it'll increase by 4 to 6 dB, and at a very high level, around 10 dB. The effects aren't quite as large with hearing impaired listeners or those with sensorineural hearing impairment. I believe the effect is around 4 dB or so, the comfortable level, and it's going to be reduced at compared to normal hearing listeners near threshold or at very high levels. Okay, that's the end of this section. Expect the following section, advantages of bilateral fittings, being posted soon.